Good evening students, welcome back to the session. In the previous lecture video, we have discussed about the electromagnetic induction. So let's have a small recap of the previous session. Electromagnetic induction, actually what it is. We know we can energize or make the electrical or electronic appliances to function with the help of a battery. Okay. And a battery is not enough to energize or to light up the entire world. So over research, Faraday has experimented the electric current generates magnetic field, the changing magnetic field creates electric current. So based on this principle, with the help of a coil and a magnet, Michael Faraday experimented the generation or creation of electric current with the help of changing magnetic field. So, with this principle, all our power stations, generators works like in the place of moving coil, one cannot make the bar magnet move here and there, so it has to be done automatically. So that setup has been replaced by the AC generator, like a bar magnet, two bar magnets in between a conductor or a wire is placed, so that based on the field change, a north pole and south pole attracts each other, and also there will be a magnetic field in between two bar magnets, and the wire which has been placed in between tries to move here and there. It tries to move in the clockwise direction, and from there we can connect a bulb, so that closing the circuit which energizes the bulb, and it gives the continuous supply of current. During this process, actually what happens, when the wire or the loop which is placed in between the bar magnet is moving clockwise, it forms a knot, and it forms a mesh over there. So as to avoid this, later during the next step of research, he found a ring, that is a slip ring setup connected with the carbon brush, and that brush is not fixed rigid. It simply slips or touches the slip rings. So as the wire which is placed in between the bar magnets moves, the slip ring also moves, and that movement in turn conveys or transfers the current produced through the carbon brush, and it forms a loop, thereby energizing the bulb, and the bulb glows, right? So the bulb glows either brighter or less brighter, or even off, based on the movement of the wire, right? Okay, so this is nothing but the alternating current. What we get from this setup is the alternating current. So as to generate a direct current, instead of slip rings, he replaced it with the split rings, whereas whenever the coil or the wire in between the bar magnet moves, it automatically contacts with the respective rings without forming a tie or a knot or any mesh. So that in turn gives the continuous supply of current, and the light glows as bright as as usual, without any change in the luminance, right? So this principle, so making the light to glow with the help of a battery is nothing but a direct supply, and whenever the voltage or the current has been induced or generated with the help of a magnet, it is called as electromagnetic induction. This is called as induced voltage or induced current. This is the basic concept of electromagnetic induction, right? So now today we move on to the concept of electromagnetic boundary conditions. What it is, what a boundary is. A boundary is nothing but two different region which meets at a point. So that is the intersection is nothing but the boundary or the interface. It is between different media. Let it be water and land, or air or glass, or air or water. Even if we keep a tumbler of water over the table, which is half filled, so that tumbler of water or that glass of water uh, occupies the glass half of the way, and the rest of the glass contains air. So the boundary between the air and the water is the interface, right? So here we are going to discuss about the boundary between two different regions. So this is, since it is electromagnetic, as we discussed before, Faraday's law experimented change in electric field induces magnetic field. Change in electric current induces a magnetic field. Vice versa, Maxwell's concepts completely deals with the change in the magnetic field induces electric current. So Maxwell uses both Faraday's concepts and this, and developed equations, four set of equations that governs the boundary conditions. So Maxwell equations are the important one to conclude the boundary conditions. And the boundary conditions are most important to solve the problems of electromagnetic waves and waveguide issues and design antennas, etc. Okay. So the boundary condition, first we will discuss about tangential electric field. Tangential electric field. Electric field is always represented as E. The tangential component is ET1. The tangential component of electric field is continuous across the boundary. Mathematically it can be represented as ET1 is equal to ET2. Continuous in the sense there is no jump across the boundary, means the electric field strength over and under the boundary is same. There is no change in the electric field strength. That is the exact meaning of continuous. It is common, or it is similar, or it is same. So the tangential component of the electric field intensity or electric field strength is same in both the regions. So here we have considered the two regions are either air or water. The next important boundary condition is normal electric flux density. Flux density is represented as D and normal component is Dn. So the normal component of the electric flux density may change, depends on the charge present on the surface. Mathematically, dn1 minus dn2 is equal to rho s, which is nothing but the amount of charges present on the boundary surface. It is a since it is a surface, it is represented as surface charge density. This is continuous, that is the normal component of electric flux density is continuous only if there is no surface charge, only if there is no current flow. Under this condition, the normal component of electric flux density is continuous. Unless it is not continuous, it is equal to the surface charge density. So the next is the magnetic component. Magnetic component, tangential magnetic field. It is represented as HT1. The tangential component of magnetic field changes based on the surface current. Surface current is represented here as K. So mathematically, HT1 minus HT2 is equal to the component surface current K, in the direction of the unit vector. So here where K is the surface current density ampere per meter, and it is the unit normal vector to the boundary. Here also, unlike electric tangential electric field, tangential magnetic field is not continuous, it is discontinuous, and by the ratio Ht1 minus Ht2 is equal to some amount of surface charge density. Here also this may be a continuous one only if there is no surface current. Surface current is absent, then this is equal, that is Ht1 and is equal to Ht2. In that case, tangential magnetic flux density will be continuous only if K is equal to 0, that is surface current density is equal to 0. Next is normal magnetic flux density. The normal component of the magnetic flux density is continuous, means unlike normal electric component, electric flux density, here normal magnetic flux density is continuous. The condition is mathematically represented as Bn1 is equal to Bn2. So these are the electromagnetic boundary conditions. Unlike electrostatic boundary conditions and electromagnetic boundary conditions, here only the electrostatic parameters like E and D, and in magnetostatics only the magnetostatic parameters H and B are discussed. Here in electromagnetic boundary conditions, all the parameters, both electrostatic and magnetostatic parameters are discussed, how it behaves across the boundary, whether it is continuous or discontinuous. So this is a small picture that reflects the tangential component electric field, and see here it is continuous, means that is parallel to the ground surface. There is no jumps or discontinuous. It is parallel to the boundary surface, as we can imagine. See here, one table is made of wood, and immediately in the consider for region 2, a glass table is placed quite adjacent with that table. If a glass of water is made to flow over the table, it flows continuously without any jumps. So this is the simple example to make you understand the tangential component of the electric field is continuous. Right? Hope you may understand this session. Thank you, students. Thank you for patience listening. See you all. Thank you.